Right, okay, in this video we're going to look at particles moving in a magnetic field, so not in a wire. Even though these ideas can be used for particles in a wire, we normally don't use them in a wire. But let's have a look. First of all, I'm going to draw my magnetic field, and my magnetic field is going to be going into the page. Now I'm using the same convention as I used before for the currents going into and out of the page, so it just represents a field going into the page this time. And we're going to have a positively charged particle moving into that field. So that could be a proton or a alpha particle or something of that nature, as long as it's positively charged in this case. So it will have a force exerted on it, the same as the charge carriers would do in a wire, except this time what we've got is we've got Fleming's left-hand rule, so my current is going from left to right, and my magnetic field is going into the board, into the page even, and you'll notice which way my thumb is pointing. That was directly up. So that direct upwards force is felt by this charged particle. But this time, the particle isn't constrained to a wire that's moving in this field. It's effectively going to be allowed to move. It's going to be allowed to be accelerated in that direction. And so, as a result, it does. It's accelerated and it changes direction. And what happens then if we look at the Fleming's left-hand rule again, we'll notice that my left-hand current direction has changed. My field is still into the page, and so look, my force is now not pointing directly up, it's pointing to this diagonally to the left. So we have that, and so it's accelerated. What about this position? Well, again, we've got our current now in that direction, and the field still into the page. My thumb is now pointing back the way it came. And so on and so forth. And what we get here is we get a situation where this particle is effectively moving. Yep, you've got it, circular motion. Now, that's really, really poignant, because especially when we look at some of the mathematics in a moment or two, because we will appreciate the fact that this force will be equal to an equation that we will talk about, plus, which is also equal to mv squared over r, which is our circular motion equation from a few videos ago. But there's a small variation that we need to talk about here, and that's what happens if we deal with a negative particle. So let's say we've got a negative particle now. So say an electron or something of that nature, or a beta particle. So we've got an electron moving into this magnetic field. Well, now you might be thinking, well, surely it just does the same thing. Well, unfortunately, no, it doesn't, because this finger represents current. And unfortunately, a negative particle does not move in the direction of conventional current. In fact, it moves opposite. And you'll know that, or remember that, from circuits when we looked at conventional current going around a circuit and electron flow. So let's just remind you of that. So if you have a circuit like this, we'll put a little resistor in there. Then this is your positive terminal and this is your negative one. Conventional current is positive to negative. That's what this is showing us. But in this case, with an electrons in a circuit move from negative to positive. So electron flow is in this direction, i.e., we're saying it's opposite to conventional current. So in this circumstance, we have to flip our Fleming's left-hand rule like that. Put the current in the right direction, And notice which way my thumb is pointing now. Remember, my current is in that direction. Field motion is this time directly downwards. And so we will observe the exact opposite of what happened with the positive particle. That when it moved into that situation, we get a circular motion, but this time in the opposite direction. So in this direction for a negative, in this direction for a positive. Now, I'm likely to come back to this in a little while, and we'll talk about how these kind of situations can change. But let's have a look at the equation now. So the equation is derived from the previous F equals BIL equation that we've already looked at. So force is equal to BIL. And we would potentially have a current because we've been dealing with a current, but for all intents and purposes, it's not a current in a wire. So we can actually define the current as amount of charge per unit time. And we can then input this equation into the one we've just got. So now we end up with an equation that is force is equal to B, Q, L over T. So, and you'll notice very quickly here, or maybe not, as the case may be, that we've got a term that's L over T, i.e. we've got a distance that's traveled in an amount of time. Well, when you have a distance traveled in an amount of time, what have you got? You get a velocity. And so we can replace this term with F equals BQ V. Now notice that I've used a little v here. That's because big V is voltage. And little v is velocity. So in this case, it's velocity. Be very sure that you make a good clear annotation of that in your notes. Q being the charge, so the charge in this case is an electron, so often this equation is wrote as BeV. And now we've introduced Bev. In the previous video we looked at Bill, and now we've got his wife Bev. So Bev is not constrained by a wire. This is charged particles moving freely. Although this equation can be applied to charged particles in a wire, so if we've got electrons moving in a wire in a magnetic field, we are saying that they are experiencing the force in this case, and we can use this equation to work out what that force would be. But it's not often used for that in this case. So with this equation in mind, let's go back and have a look at our previous diagram. So force equals BeV or BQV. Okay, so when we look at this situation very carefully, we can observe the fact that something is going to change when we change some of these values, B, Q, V. So let's look, for example, what would happen if we changed the velocity? Well, if we change the velocity, it's not going to be moving as fast, and it's also, as a result, going to reduce the force. If we reduce the force, we would expect a very different situation to occur. We would expect a more eccentric circle, because effectively what's happening here is it's not being accelerated as quickly, and so the force that's making it turn is not as great, and so as a result we get a much wider circle produced when they're not moving as fast. So in order to make sure that we have a nice small circle, we need a nice fast velocity. Well, that's what happens when we change the velocity, or decrease it in this case. What about if we change these values? Well, we will observe a very similar thing. If we decrease the charge, so if we used a smaller charge in this case, then we would expect a lesser force and hence a bigger circle. If we decreased the magnetic field strength, we would also experience a greater size circle. Now, this is pretty much the entire principle behind a hadron collider, where they move charged particles in a circle. So in order to make that circle as small as possible, we need to make them move as fast as possible, so we get a nice big centripetal force acting here. We need to have really strong magnets, but unfortunately the charge of particles tends to be fixed, but depending on what particle you're using depends on what size ring you end up needing to use too. So decreasing V, bigger circle; decreasing Q, bigger circle; decreasing B, bigger circle. And so as a result, the opposites will be observed: bigger V, bigger B, smaller circle; bigger Q, smaller circle; bigger V, smaller circle, because of the relationship of this equation. So we'll hopefully look at this equation and put this together, and we're also going to start looking at combining this idea with electric fields as well, to see if we can, instead of getting particles to move in circles or parabolas in the case of electric fields, we can actually get them to move in a straight line. We can combine them, and that's for the next video.